Now we are going to look into another example, which is question 46C. You are given two polynomial equations, 6 minus x squared and 1 plus x plus 4x squared, and you want to check whether these two polynomial equations are they linearly independent or not. So using the same formula in the previous example, you multiply it with a constant, and you want to check whether this equation, where the scalar multiplication with the polynomials and the summation of them equals to a zero vector. And you need to check, and you need to prove that the scalar for the x0, x1 and x squared equals to 0 for the system to be linearly independent. So by inspection, we know that there are two unknowns, which is the a and the b constant. And there are three equations here from the coefficient for x0, x1 and x squared. By inspection, we know that we have one extra equation, and most probably this equation is redundant, which means that either one of the equation can be combined. Either one of the equation can be produced or generated from the combination of another two equations. And I'm going to show you how does the row reduced echelon matrix form will prove this assumption. So you have this system of linear equation where you take up all the coefficient of the x0, x1 and x2 and you put it into a system of linear equation. The matrix of A is 6, 0, minus 1 and 1, 1, 4. And when you put it into an augmented matrix form and you reduce into a row echelon form, so you get this 1, 0, 0, 0, 1, 0, 1, and the last row becomes 0. So here you get the values of A equals to 0 and B equals to 0, which prove that the zero vector system here exists, and the given two polynomial equations, they are linearly independent. Okay, the last row, you obtain a row with all zero entries, which means one of the equations is redundant and extra, or can be combined or generated from the combination of another two equations. I'm going to show you what does it mean. So just look at this equation. I label it as the first one, the second and the third equation. The third equation can be produced by the combination of -1/6 multiplied with the first equation and plus 26/6 multiplied with the second equation. Similarly, equation number 1 can be produced from the combination of the equation number 2 and number 3. -6 multiplied with equation number 3 plus 25 multiplied with equation number 2, and you will get this answer. The first equation. And I left it for you to check how do you get the vector, the equation number 2 from a linear combination of equation 1 and 3. And this proves that our expectation or assumption is correct. We have one extra or redundant equations where when you put it into this matrix system and row reduce it, you'll get a row with all zero entries. Okay, clear? And remember from the previous example, we learned about the rank and the nullity. The rank here refers to the number of leading one at the column or row. So we have two rank. And nullity refers to the number of parameter solutions. And remember the relationships between the rank, nullity, and the number of unknowns. The formula for nullity is the number of unknowns minus the rank. In this case, we have 0, and we don't have a parameter solutions here.